Okay, I think we should start because one, we already told people DP isn't really necessary for internship interviews and stuff. And two, we're actually behind time. So what we are going to do is we're first going to start with just something simple on matrix manipulations, and then we go on to dynamic programming very quickly. And for the matrix one, um, we just do a part of it and then we just continue Godolin next week. So there's just a few properties of matrices which I think we should which I think help if you have them in your mind. So let's first consider a matrix. Wait, give me a second. Uh so in programming in general, usually like programming questions, matrices usually are used in two forms. One is in their normal form as matrices, and the second is in the form of graphs, right? To show relationship. So we are first going to consider in their normal form. So let's see, we have, wait, give me a second. My pencil is not connecting. Okay, it's connected now. Well, wait, give me a second. Okay. All right, so assume you have this as a matrix, right? And matrix questions used to like be scary. Like in 2021, I did this online assessment by Goldman Sachs, right? And I had this question that was to sort matrix diagonally. If I remember clearly, it was about 2 years ago. And at that point, I really hadn't done a matrix question or something, so it was really brutal. So it was later when I was done, I went to like review like how matrix manipulations actually work. So I think it's really good to know. So matrices are usually represented as nested lists, right? Nested arrays. So this one is going to be represented as let's use a different color. So this is a row. So this is going to be as one list. This whole thing is going to be one list. This is going to be one list in the array, right? In the nested list. This another, and so on and so forth. And this one is, let's say, the main list like this. You're going to have something like this, the main list. And then the red one comes in as this, as a list on its own. Then comma. Let's say the second one, which is this one. This one you see here will come in next, like this, and so on and so forth. Like this one will also come in like this, right? That's how basically they are. So to basically go through, there are two ways to iterate through this matrix. One way is to take a particular row, right? So you're going to take this row, is to take a row. So going here is a row, and coming down here is a column, right? So matrix go here. So this is a row, this is a row, this is a row, this is a row, and this is a row. And here is a column, right? A column. It's good to learn how to traverse them column-wise. In other words, to be able to go row by row. So you take this first row, then you take each of its elements, right? Then you come here, you take each of its elements. That is the row traversal, right? Going through it using the rows. It's also good to know how to do it using the column. So you take the first column, that is this column, take its elements like this, and then you go on to the next column and so forth. So let's first do the row. So usually what we do that we get the length, the number of rows. The number of rows is equal to the number of lists, right? So here there's one list, there's two, there's three, there's four, and there's five. So to get the list, we can simply do the length of the board. Let's assume it's a board or matrix or whatever. Then the columns usually is like every row has the same length, right? So the column length is simply the length of the board index 0. So that simply means that take the first row, or it can be any of them, honestly. So take any row, right, and count how many elements there are. So if I take this first one, the number of elements are 1, 2, 3, 4, right? That means there are 4 columns because every row, they have the same length, right? So if I take the first one and just count how many elements there are, and it's equal to how many columns there are. So like each element, right, represents a whole column on its own, right? So you get the rows and you get the columns. Then what we do is that we just use a for loop for every row in range rows, right? Then we just going to say for every column in range columns. Now note that R and C are just like variables, right? So R is just going to be like, so let's say for this one, there's 1, 2, 3, 4, 5, 6, there's rows is 6, right? and this one is also 4, right? So when R is 0, so at the start, we're using range, right? So range rules means that R is going to be 0, 1, 2, 3, 4, and 5, right? So for R in range, so when R is 0, right, we're talking about this first row. I hope that makes sense. So to get the element here, we can simply do that element, let's say EL, is equal to our board index R, index C. So that's like index R means take the current row, right, where R is standing at. So let's say R is at 0. So take this current one, right? Then index C. Index C2 is 0. So take the first one, right? So elements in a grid are accessed using, the two positions, right? R and C. So board. So if we have board of 2, let's say 3, it's like go to row 2, right? Go to row 2. So 0, 1, 2. Go to row 2. And now you're here. Once you're here, go to column 3. So column 0, column 1, column 2, column 3. And that's how you get the elements here. So that's basically how they work. So this is basically how we traverse it row-wise. So you take a row, then you go through each of its columns, and then you are done. If you want to traverse the matrix column-wise, you just take this one, right, and bring it to the inside and bring, the column one outside. This is what I mean. So for that one, you do for column in range of columns, right? That's like, if you take a column, then go through its rows, and then for row in range rows, and this will traverse it row-wise. It's really good if you try to like write it out yourself and see what happens. So that's, but like saying for column in range columns, so that's like take the column, right? So if its column is equal to 0, you mean this column, right? Then take for every row in the column. So there's a column, and we said if you go here is row. So you take the column, like the first column, then you go through it like this. That is going to make you do it a row-wise traversal. Now, some properties of matrices, which are good to know. Let's consider the diagonals first. So if you take a matrix like this, right, or a board like this, I just want to show you something. Which if I knew, I could have solved that question then, but obviously I didn't know. So this is column 0, column 1, column 2, column 3, row 0, 1, 2, 3, 4, 5, right? Let's consider the diagonals. You realize that there's something crucial about the diagonals, right? If you take, let's take one diagonal as this. Let's take a couple of diagonals. This is one diagonal, this is another diagonal. It may be a bit messy, but just follow me carefully. This is something good to know. Even if you do the n-queens problem, it's something you use, right? Let's take the diagonals. There's a property, right? That all the diagonals, now let's take any diagonal. Let's just choose one. Let's choose this long one, this long one. Can everyone see this long one I've chosen here? This long one. Let me use a different color. This long diagonal here. Right? Let's look at this long diagonal here. And let's see the cells that make up this diagonal, right? So if you take, so this is one cell in it, right? And the row, right? The row is 3 and the column is 0. So we get 3, 0, right? So that's for this box here. That's 3, 0. Let's take this box here, right? That is row 2, column 1, 2, 1. Then you take this box here again, right? And that is row 1, column 2. Then you take this one to here, row 0, column 3. Now, if you add these, you realize they're all equal to 3, right? So that's one thing you should know, that for diagonals, right? For diagonals in the matrix, always, if you add all the elements of the coordinates of a particular diagonal, they are the same. So when you choose this diagonal, if you add both the row number and the column number, you end up getting the same value, 3. So if you have a question, they ask you to do something with the diagonals, and they're like, how can I get the diagonals? It's simple. You can simply, just use, a hash map or something, right? We can simply use a hash map. Where the key is the sum you get if you add the row and the column, right? So here the key would be 3. And the value, it's simply, those elements, which one added are equal to 3, right? So like a list or something, like some collection, right? Let's take a different diagonal and prove it. Let's take this diagonal here. Right, let's take this diagonal. So if we are here, right, this is 5, 1, right? This is 5, 1. So we have 5, 1. Let's take the next one, right? This is 4, 2, right? This is 4, 2. And this is 3, 3. And we're like, when you add all of them, you get 6, right? each of these is equal to 6. And that tells you it's a different diagonal, right? So that's how actually you get diagonals. Anti-diagonals too are the same. That is like coming this way, right? They're actually the same. So that is one thing you should know about matrices, that for elements across the same diagonal, if you add their row number and their column number, you actually get the same value, right? So you can let the value, right, be the key of the dictionary. And as you are looping through it, right? So as you're looping through it this way, right? So inside your for loop, you're like, if R plus C in dictionary, just append the current row, comma, column, right? Else just create a new entry, and that's it. The next thing to know about matrices is actually traversing them in 4 directions, which we'll go through. I don't know, we're actually behind time. I want to start DP. So what do you put things? Should we touch on that? We can't touch on the graph matrices yet because quite a number of people didn't come, and I want to still do DP. So do you think we should talk about the using 4 pointers on the matrix? Should we do that now or go on to DP?
Yeah, let's do that now. I'm curious.
Okay, let's do that now. So let's assume we have, so please don't forget these properties we just mentioned, right? Like it's very important. The column wise and everything. I didn't know that, just later I learned it. So let's do this. Let's say you have, actually we can use a certain famous question to go through this. Rotate image. Let's look at it carefully. Okay, so assume we have this grid, right? And let's just push in some numbers very quickly. Oh, shoot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, right? And now what we want to do is look at this carefully. What we want to do is we want to kind of like rotate, let's use the rotate image problem. We want to rotate the image. So by rotation, this is what we mean. I give myself too much work here. Let's just change this. So by rotate image, this is what we mean. You know what? Let me just use as a 4, what do you call it? A 2 by 2. No, a 2 by 2 is too simple. Let's use a 3 by 3. Yeah, a 3 by 3 will work well. 1, 2, 1, 2. Okay. Then let's fill in the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you rotate, what they want is the 7 to be here, right? The 1 to be here. Then the 3 to be here. Then the 9 to be here. Then the 8 to be here. Then the 2 to be here. Oh, what did I just do? Then the 4 to be here. Then the 2 to be here. Then the 6 to be here. Then the 5 to be here, right? So if you look, we've actually rotated this image. But how did we rotate the image? So it's like you took this, what do you call it? This row, right? And this whole row became a column here, right? Can we see it? Like this row became a column. So this row became a column, right? Then this column, right? This column became a row here. Can everyone see what's happening? Please do want to take a look at it and understand before we move on. If you want to pause or something, just let me know, right? So that's like the row, right? This row here became like the column here. So it's like you're doing that thing. What do they call it? I've forgotten the name. The Rubik cube, right? And like you're moving the things around, right? Like the row becomes the column, right? The column becomes the row, and so on and so forth you go. Does it make sense?
Yeah.
Good. So usually what I do with questions like this is we initialize our 4 pointers, right? So what we can do is that let's do something here. So this is going to be a left, right? This is going to be a left pointer. This is going to be a right pointer, right? This is going to point to the top, right? The top, call it T, and this is going to point to the bottom, right? So with these 4 pointers initial, and you can easily find like where all these, like you can easily find the positions very simply. You can simply say left equals top equals to 0, right? Both the left and top are 0, right? Because top is at row 0, is pointing to row 0, right? Top is pointing to row 0, left is pointing to column 0, bottom and right, right, are both pointing to the last one, right? So that's like length of maybe board, right? They're both pointing to the last one, right? So this is like -1, right? So that's like position 2, this position 2, column 2, and this is also, row 2, right? So that's basically how you initialize your 4 pointers, right? And then what we can do is that we can simply get bored, right? We can get bored. So we're going to perform 4 steps, right? Because if you saw, it's the movement's actually 4, right? Let's look at it. So it's like take 1, right? Let's look carefully. Take 1, right? We take this one, bring it to where this guy is, right? Then we take this guy, bring it to where this guy is, right? So you've done 2 steps now. Take this guy to bring it to where this guy is, 3 steps now. Take this guy, bring this guy here, 4 steps now. And after that, you are done. Then we can move the pointers, right? So these pointers are kind of like helping you, right, know where to take the elements and where to put the elements. So if we look at this, let's make it clearer. So if we look at this right now, if we take this one, right, we already know the position of this one. Somebody can simply be like, oh, this is board. So the row first, row is T, right? And the column is left, right? We will take this guy, right? And then we will bring it here, right? We'll bring it here. How can we get the position of the element here? That's also simple. By looking at it, you can see it is also board, the same row, right, as the first element, this one. So again, row T, but the column is what? R, right? Now, so we bring this one here, fine. Then we take this guy, and then we bring that guy also here. But you know we can easily get the index of this guy too now. It's simply board of B, that's the bottom, and then left, oops, is right. Then you take this guy to here, you want to bring this guy here, but you know the index of this guy now, right? That's also board, bottom of right? So it's these 4 pointers help you to easily find the positions, right, of the elements at these positions, right? And assuming you are done with this swap, what do? Now you just need to move on, you just need to adjust your, what do you call it, your pointers, right? So the left pointer, so that's like we have here, left and right here, and you had top and bottom here, right? So when you are done, all you have to do is to move each of them. The left one is going to move here, then the right one is going to move here. The top one is going to move down to here, then the bottom one is going to move up to here, right? So now you have your pointers here. So this is where our pointers are, right? And we do the same swap again. Take this guy, right? You take this guy, then you bring this guy here, right? You bring this guy, wait, let me see my diagram well. Yeah, that's correct. So we take this guy and we bring this guy here. I think so. This will come here. Yeah. You can take it and you can easily get the index of this guy, right? The index of this guy is very simple. And then so on and so forth, and then you go. So if you look at this, the condition stops if left is less than or equal to right. You can even make it less than right, and that would equally work. So that is one thing about matrices. You can initialize like 4 pointers to be at the 4 positions, and then you move them in as and when you like. We make if we have time, maybe going tomorrow today, we'll at least do 1 question on it. But I don't think we do. Okay, now let's go to DP. And as we said from last week, dynamic programming is one of those things, one of those concepts that doesn't have like a fixed pattern, right? That's like, hey, we do everything this way. And it's not like, yeah, Jesse, you have a question?
So I want to know for DP, does it require you to have a knowledge on recursion and memorization?
Oh, I'll come to that later. So there are two ways of solving DP problems. You have the bottom up and the top down. Top down is typically recursion, and bottom up is simply loops. So as the last time you mentioned, we said that everything done with recursion can be done with loops, right?
Okay.
The contract is actually not necessarily true. It's not, I don't know, but some people say everything done with loops can be done with recursion. It may be true, but right now I hold the right to say that's true because I feel like loops are too basic. So yeah. So as I was saying, DP is one of those concepts where there are different categories of questions, and the more you study certain of the questions, the more your brain is able to solve new ones, right? Like it's like the questions are into classes, right? So like if you take like the DP family like this, they're like different classes of problems like this, right? Like the different approaches that people spend their whole lives in school trying to figure out problems, right? And how to solve them. So people like find maybe 50 problems, and they're like, oh, these 5 are related, right? Oh, these 7 are related, these 18 are related, and so on and so forth, right? That's the life some people are doing right now. you know, algorithmic, what do you call it, theoretical computer science. They try to find problems. I'm like, how am I going to solve this problem efficiently, right? So if we have something called the P and NP problem, computational intractability. So DP, there's no one coming like, I'll teach you the whole of dynamic programming and stuff. No, your best bet is to try as many problems as possible. And then, if you get a problem that falls into that same bucket, then you're like, oh, let's go, right? So that's basically what we do with it. So now you're going to take one bucket and just look at that bucket. And now I'm going to use a very slightly difficult one, which I think it's good to know. So this is a problem we have here. So let's assume you have a collection of intervals, right? You have a collection of intervals like this. A collection of intervals like this. Also, we did the NASA question last week. There's one answer. You can actually use DP for it, depending on the variant. But I want to change the question today. So let's look at this question we have here. And now the question is simple. Think of these as intervals, right? And let's say they have a scale here, right? Let's say they have a scale here. And the scale, I just remove this. And the scale is, let's say, at 0 here and at 10 here, right? Let's say the last one is 10. And I want to find how many of these intervals can we choose without any two of them overlapping, right? So the question is called non-overlapping intervals, right? But the question is, how many intervals do not overlap, right? We want to find the longest selection of intervals such that none of them overlap. So let's just give some markings here. So this is 1, like this guy is pointing to 1. This is pointing to 2. It's not even, but let's just take it like that. These two, assume these two guys are the same, like these two guys are pointing to 3, right? This is 4. This is 5. Actually, these two are 5. This is 6. And then this is 7. Wow, I did the thing perfectly. Well, almost perfectly. This is 8. Oh, it is perfect. This is 9. And this is 10. So just want you to look at it and tell us how you think you can do this question. We're going to choose the longest chain of longest non-overlapping intervals, the longest chain of non-overlapping intervals. So for instance, if I chose this interval, right? If I chose this guy here, and I chose this guy here, and I chose this guy here, I would get 3. But the question is 3 the longest I can get? Somebody's like, if you choose this one, you get just 1, right? Which is 3 is definitely better than 1. How do you think we can do a question like this? How do you think we can do something like this? How do you think we can do something like this? How? Don't think deeply, like don't think anything. Just like normal English, just a normal algorithm or something. How do you think we can do this question? How? How do you think we can do this question? I'm waiting for someone to talk before we continue. Don't think of code. Don't even think code. Like just an algorithm, right? Like become like, hey, take this one, then do this. Take this one and then do this. Yeah. How do you think we can solve this problem? Also, I'm giving the intervals labels to make our lives easier. So anyone, how do you think we can solve this problem? You want to choose the longest number of non-overlapping intervals. Anyone? So assuming you're choosing a course, right? You're choosing a course in school in the semester, you want to take as many courses as possible without the timestamp of any overlapping, right? No conflicts. How okay, here, okay, first of all, which courses will you choose here? What will be your answer here? What will be your answer? Anyone, what will be your answer? What will be your selection? Okay, someone has put something in the chat. Let me check. Okay, ADG. Okay, good. Yeah, ADG seems to be the answer. Good. Yeah, so how do you think we can get ADG? Yeah, how do you think we can get ADG? Okay, so let me show you one way we can get ADG, right? There's a couple of ways, like 2 ways I can think of right now. Oh, was someone talking? Okay, so one thing we can do is that so this diagram I've given you is one thing I want you to put in your mind. Sorting interval. We have intervals questions. Almost always we sort them. You sort them by the start time, right? So when you sort them by the start time, you get something like I have here, right? Many of the questions because when I give you the questions as input, they don't give it to you this way, right? They don't give it to you like in a diagram. They give it to you as a list, right? If they tell you sorted fine, they give you like here, they'll give you something like 3, 5, then they give you like 1, 2, and everything. But you see, this is not equal to what we have here. So almost always intervals question, we sort. So don't forget. Okay, so what we can do is that 1, we sort it so it appears as we have here. Then 2, I'm going to do one thing. 2, we can take an interval. So let's say we take A, right? We take A. Then we can remove, right? We can remove all intervals that conflict with A, because now we can't consider U. So if I choose A right now, right? So let's assume we choose A right now, right? I'm going to remove all intervals that conflict with A. So that means I'm no longer going to consider B, right? So B can no longer be considered, right? Then, so after I've removed all those intervals that conflict with B, then I'll choose, so now I have D and C and all these ones. Then I'll choose the next interval, right? Then I'll choose the next interval. So here, I have a conflict between D and C, right? I have a conflict between D and C. Can everyone see? I have a conflict between D and C, right? Can everyone see? Like both D and C starts at the same time, right? So the question now is, which one do I choose?
Yes.
So which one do you choose? Between D and C, which one do you choose? Between D and C, which one will you choose? So you've chosen A, then you move all intervals that's conflict with A, right? And these are the remaining ones, right? You don't even think of D and C. Which one should we choose? So now we have D, C, E, F, G. Which interval should we choose? We want to find the longest chain eventually. Which one do we choose?
We'll choose D.
Good. Now, why will we choose D? Why? Why not C?
Because it is shorter than C.
Exactly. So you want the longest chain. So I want you to end first so that the probability of me getting someone else is very high, right? So that's what we do. That is simply what you do. So, yeah. So here you'd have chosen A. We choose A. Then we remove all the ones that conflict with A. Then we choose the next interval. We've already sorted them, right? So this guy and this guy will start at the same positions. But if there's such a conflict, right? If there's such a conflict, choose the one that ends first. So when you choose, so here you've chosen A and D. Then for D to remove all intervals that conflict with D. So C will be removed, F will be removed, E will be removed, right? Then the last thing you do, G is the only one left, then you choose it. So you found one, so you record the length down as length 3. You have 3 right now. Then you do the same thing again. You choose B, right? And remove all intervals that conflict with B, right? So here, that means you remove D, you remove C, right? And then you're left with this one and this one. Then you down to you get length, I think 2. Then you do the same thing for every single interval, and then you're done. So that is the algorithm. Does this algorithm make sense? This is not DP. This is what we call a greedy algorithm, right? This is a greedy algorithm. Where you simply want to find the length of the longest overlapping interval, and then you are done, right? And so a greedy algorithm has something called the greedy rule, right? And the greedy rule is what you use to make the decision. So here was a greedy rule. A greedy rule is that when you take an interval, right? So first you sort the intervals definitely, but when you take an interval, you remove all overlapping intervals, right? And choose the next interval that has the earliest finishing time, right? So when it was between D and C, we chose the one that finished earliest, and that was a greedy rule, right? So that is greedy greedy simply means it doesn't look so much into the future, right? It just cares about what is before it and to be greedy and just make a decision, right? So here we are like, hey, if it's between D and C, the rule I'm going to use it, just choose the earliest finishing time, and then you are done, right? And that is basically it. So that's how you can find the longest non-overlapping intervals. But then let's change this question to dynamic programming. Now, what if we told you that each of these guys, right, like each of these intervals, right, and even this greedy rule I told you, that looks like O of n squared, can actually make it O of n. Let's say we can make it O of n. Make it O of n. After you have sorted it, right, just choose the intervals with the earliest finishing time, and that will also give you the same answer. So if you want to look at this, if you choose A as the earliest finishing time, right? So I choose A. Remove all intervals that conflict with A. Then these ones are left. Choose the earliest finishing time again. Choose D, right? Then remove all that overlap and you choose G, right? So you realize that all you need to do is just one pass, right? Just one pass through. Then simply use a heap to do it. Because if you heapify this, right? If you heapify this, after you heapify this, you can simply just use one pass through, and that's O of n, right? So it's actually O of n time. And yeah, now let's make it DP, right? So here we just considered one chain, right? A, D, G, and whence. And the greedy rule was always choose the earliest finishing time. A is the earliest finishing time. Then you move all that overlap with A, then choose D, earliest finishing time, and G, earliest finishing time. One we can think of this question is, you have a certain machine, right? And you want to put jobs on that machine, right? You want the machine to do work for you, right? But you want the machine to do as many work as possible. You don't care. All you want is as many work as possible. So what do? Put on the job that finishes first, right? Because this job takes like just 3 units of just 3 hours, just 2 hours. So it'll finish first and then we'll get more. But now let's make it tricky. Now we're telling you that every job, right? Every job has a certain, value, right? In other words, this job has value. Let's change the numbers. This job has value. Where's black? Has value, let's say 2. This will give you 2 Ghana cedis, right? This will give you $10 US. This will give you $5 US. This will give you $12 US. This will give you $15 US. This will give you $3 US. This will give you $6 US. And they're asking you, which jobs will you choose now to maximize your money? So you see, the questions are different. The greedy algorithm one, we are like, choose as many jobs as possible. There was no value assigned, right? So that's like, oh, I just choose the jobs that end first. So you choose A, you choose D, you choose G. But then they're like, every single job has a value assigned to it. So which one are you going to choose, right? And at this point, you're not a magician, right? All you can think of is, well, if you go back to the backtracking we had, right, you're going to try all possible combinations, right? So you're like, if I choose A, so we start one, right? If I choose A, what jobs can I choose next, right? If I choose A, you cannot choose B, right? So we have something like this. The total is A, B, C, D, E, F, G. Also, you're like, if I choose A, right, what other jobs can I choose, right? It's obvious you cannot choose B, but you can choose between C and D, right? Now, between C and D, which one will we choose? Between C and D, which one will we choose? Let's make this 15. So we've chosen A. Which one will we choose? We've chosen A. Which one will we choose? We can choose B, right? Because there's a conflict there. Okay, let me check the chart.
D.
D. Why will we choose D? Why are we choosing D? Let me do something. Why are we choosing D? Why are we choosing D? Can anyone tell me why we are choosing D?
It doesn't conflict.
It does not conflict, yes. Then I actually made a change. So now D is 12 and C is 15. Yes, it does not conflict, but then C2 does not conflict, right? So the thing is, so if somebody looks ahead, right, the person will be like, choose C, because C has value 15, right? And D has value 12. Can everyone see it? Because now the deciding factor is also the value you get from the job, right? Like the money you get. From D, you're getting only 12 Ghana cedis, and from C, you're getting 15. You want to maximize your money, right? So you're like, okay, let's choose D. But if you choose D, someone will be like, you're making a mistake. But the thing, can tell the person, what if in future, by choosing D, right? So like if you choose D, you can choose G in future, right? But you don't know the value of G now, right? So it's kind of like, let's do this. What if something happens, right? Because I have to try all possible combinations, right? Because currently, in this current setup, it will be better to choose C, right? A and C, because what do you get? If you choose A, you get 2. If you choose C, you get 15. What's the total? $17, right? Or 17 Ghana cedis, right? But then if we chose D, we'd have chosen 2, 12, and 2, and that would be 16. And obviously, this guy was better, right? Does everyone get this argument? Does it make sense? Does this argument make sense? Does this argument make sense? Good. Then what if this was also 12, right? What if this was also 12? That also means that you can't just compare like this D12 and this C15 and then make the choice, right? Over here, it looks like someone will be like, let's choose C because 15 is bigger than 12. But then you don't know that in future, 12 will allow you to take G. That is another 12 here, right? So it's like there's so many possibilities. And that's when dynamic programming comes in, just like the backtracking we did. You have to try all possible combinations. So like the tree we saw last week, right? So you're indeed going to get to a case where you try A. So there's going to be a branch for A, D, and G. There's also going to be a branch for A and C, right? So there's going to be these multiple branches because you don't know yet. Then after you've computed the total value, you return everything here. And then you make the decision. You simply take the max. Let's say this is branch 1, this is branch 2, and you simply return the max of branch 1 and branch 2, right? So this is actually what is going on. So for dynamic programming, we actually try all possible cases, right? Because you don't know which one is going to give you the value yet. And then, does this intuition of dynamic programming work? We've not gone to don't think of memorization now, right? So with greedy, we could easily make a rule, choose the one that is finishing first. Once you add values to the jobs or to the intervals, then it becomes tricky because you can't tell the future, right? And the only thing is to try all possible combinations, right? Does this premise make sense? Does this make sense? We are now going to go into memorization. Does this make sense? Does this make sense?
Yeah, it does.
Good. Now let's go on to the next thing. What is
I wanted you to go, but there's no time.
Don't worry, when I'm going to the next one, I'll actually repeat a few things, so no problem. Now let's look at something here. Let's assume, right, that now somebody has done a good job and they have done let's see. I want one my diagram. Let's see. I want two paths that is like the same thing. A G, let's say B D E. Let's say C. Let me do something a bit. I just want one path that shares something, right? See, let me make this guy. I'm just making this guy and this guy not overlap, right? I just want to show something, but I can't redraw everything from scratch. So let's say this guy is like this, right? Sorry, I just changed D. So D and B do not overlap, right? They made that change, right? So let's see. So let's see we're done with the A branch, right? So for A, we've done A, we've considered A, D, and G, right? So let's say we are done perfectly, right? And now let's start. I need to give me a second. Okay, now let's proceed. So now you're not ADG, right? So we are actually done with this part, right? Now we are thinking of, we're now going to dynamic programming with memoization, because now it looks like I have to try all possible combinations, right? I have to do A, D, G, because I have to do A, you know what, A, C. I have to do all these combinations, but then DP will allow you, right, to not create the whole recursion tree. Like you don't have to create the full tree. Sometimes by computing for one branch, you can reuse its value for another branch if you get there, right? So let's look at that. So you've done ADG first. That was the first thing you tried. That is good. And now let's assume, right? So that one you started from here for the jobs to be picked, right? Started from here. So you ignore those that conflicted with B. But now you start from B. So you start from B2, that means you have to ignore A because A conflicts with it. So we actually ignore A. So we add B. Then like, okay, so you can't also do C, right? Because B and C conflict. So you ignore C, right? We ignore C. So C is not possible. So let's say D is the next one. D is the next one. But the question is, should we really compute, D, right? Should we compute D? That becomes a question. One, I know I've already had a branch that had D in it, And the answer is no, you don't have to. We can simply take that value of D we had here, right? Let's change the color of D we had here, right? And just bring it to the B. So here we chose B, and B, we are like, go to D. But you're like, no, we've seen D before, right? So let's just take that value of D and bring it here so that we don't make any more recursive calls. So all this does not happen, right? So with DP, when you get to a subproblem, right? And you're like, have I computed this subproblem before? You're like, yes. Then don't compute it again. Just go and borrow that value and bring it in, right? To make all this formal, right, and all this clear, let's be a bit theoretical. So what we do is that we do DP, right? So you're just going to do a letter, right? DP of a letter, right? DP of some letter. So let's say A, right? DP, let's just use X. DP of X is simply going to be the maximum value obtained if I start at this job. If I start at this job. And this English I'm actually giving is like so important when solving DP problems. Always define the thing. DP of X is the maximum value obtained if I start at this job. So let's look at what we mean here, at this job. So when we're doing the A branch, our question was, what is the maximum value I can get if I start at job A, right? And it's like, okay, if you start at job A, you can do A, you can do B, right? You can do D and G, so you can do A, D, G. You're like, okay, but someone's like, okay, you can also do A, C, right? Then, so you have two things now, right? Two things that have here, and then we chose the maximum, right? And that maximum is what we are going to return. So here, DP of A, right, is going to be the maximum value of, is going to be the max of AC, right? That branch, and ADG, that branch, right? So that's actually how it's done. Then someone will be like, okay, so I'm done with A. Now, let me compute DP of B. And DP of B in English simply means that what is the maximum value I can get if I start at job B, right? And it's like, okay, if you start at job B, it's going to be equal to, so let's assume we are taking the branch B, D, G, right? So it's going to be, the maximum value I can get from B depends on the maximum value I can get from D. It depends on the maximum value if I start at G. The maximum value you can get if you start at G is simply 12, because 12 is the last one, right? Then like, what's the maximum value I can get if I start at D, right? And that's going to be the DP of D plus the DP of G, right? And then the DP of B is simply the value of B plus the thing here. So to make it all clear, DP of X is simply equal to the amount at X, right? So let's just call it X plus the DP of the next one you choose that does not conflict with X. Let's just call it PX. And once you have this recursive relation, that's solving this question. That's how you solve DP problems. This is what we call a recurrence relation. A recurrence relation, which is kind of like, if you saw, it's actually recursion. You have DP, I assume DP is a function, right? Because we said DP is the maximum value obtained if I start at this job. So DP of X is a maximum value I obtain if I start at job X, right? And P of X is the next job that does not conflict with X, right? P of X is next job that does not conflict with X, right? So you see, this function DP is being called here again. That makes it recursive. We're actually out of time. We'll go over this again, but I just want you to have this intuition like in your mind that with DP, you try all possible branches, right? But then to not make it, all possible branches is actually going to be 2 to the power n, right? Because as we discussed last time, if there are like n elements, they're going to try all possible combinations, right? All possible combinations, like number of subsets, right? Is 2 to the power n. But 2 to the power n is super inefficient, right? But when you memorize, when you catch, as you saw here, we wanted to find dp of d, right? So here we saw that dp of A, when we did the branch A, is equal to dp of B, right? This branch is equal to dp of D, right? Plus dp of, what did we choose again? dp of G plus the amount at A, right? And then we also saw that is when we chose this job, right? When we chose this job, it was A, D, G. Then we're like, now what if we start at B? So we are like dp of B, right? It's equal to, so for B, we are like, okay, we can, from B, we can do DG, right? D2 can do DG. So we are like dp of D, follow this carefully. This is the last part that we are done. dp of G, and then the amount at B, right? So this is basically okay. So now let's read it in English. I said reading deep in English is so important. So here you read the English as dp of A is the maximum value obtained if I start at job A, right? At this job A. It's equal to the maximum value I obtain if I start at job D plus the maximum value. Actually, it should not be plus. It should just be, sorry, it shouldn't be plus. It's actually a recurrence relation. Sorry, I made a mistake. Sorry. My brain is a bit, it should be, sorry, it's not plus. That will just, so it's equal to A plus the maximum value I get if I start at D. And that maximum value you start when you start at D is equal to D plus the maximum value you get if you start at G, right? Please, does everyone get this? I don't know, I hope this is not confusing. Look, dp of A simply equal to A. So this is a path. It's like this: A, D, G, right? So I'm like, the maximum value I get at A, right? It's simply equal to A plus the maximum value I get at D, right? The maximum value you get at D is equal to D itself plus the maximum value you get, right, when it starts at D, right? So that's basically what it is here. So dp of A is simply equal to the value at A, right, plus whatever value you got when it started at D. And whatever value you got when it started at D is simply equal to D itself plus whatever comes after D, G, right? Please, does this make sense? This is a recurrence relation. Does this make sense? I want this thing to make sense, like this thing to make sense. This to make sense.
Yeah, it does.
Yeah, it's just like recursion, like,
Yeah, it does.
yeah. So we can do the same thing here when we expand for B, right? So if I want to get for B, so right now you can think, so the two ways, you can think of it bottom up, right? So bottom up is, so this is what we did is actually top down, this top down, like dp of A. That is the first point where we want to get to, like from the tree, right? This is what we want to get to. We are like, what will I get if I actually started at G? And G is the last one, so you're like, oh, it's G itself, right? Then you bring that value here. You're like, what if I started at D? And this, like, the value you get is the value you got at G plus my own value, right? So that's what you have at D now. Then you're like, what if I start at A? D, A is like, the value you get is what my own value, that is A, plus what you got at D, right? So it's like just bubbling up. So this is what this bottom up. And top down is you coming down. So top down is recursion, bottom up is for loop. You can simply use a for loop to compute this, right? So let's look at this one, and then we see that the similarities, that's the memoization. So you're like dp at B is simply equal to whatever value, whatever money B is giving you, plus the next interval you chose, right, from B. So that was also D. And the value you get for here, right, is also equal to D itself, right, plus dp of the next one, G, but you know, G is like a base case. G is like after G, there's no one else, right? So as you can see, there's a similarity, right? Like dp of D is here and dp of D is here. So if you've already done this, right, if you've already computed this path ADG, and then now computing for path BDG, you don't need to compute dp of D again. And simply go and borrow the value from here, right? So you don't go down that branch. And that's what we call memoization. So if you look at this in a tree form, it's like this A, D, G. Then, you know, that's one part. Then there's like B. So this is like the roots. Then there's like B, D, G, right? But if I've computed this, I don't need to compute this, right? I can save all the recursive calls here. Just take the value for D and just come push it in here. That's what we call memoization, and that is all, right? Does this make sense? Wait, are we confused? Is anyone confused? Jesse, are you confused? Wait, is anyone confused? We're actually not going to do anything extra.
Yeah.
I just want you to have this definition of
Okay, I have a question.
yeah.
So you said using a for loop, right? That one
Yeah.
is top down, or is it bottom up?
For loop, we use no loop is actually bottom up. I'll actually show you a question like that if you want to
And-
see it. Let's say we have
And
this.
recursion is top down.
Yeah, recursion is top down. We all know the Fibonacci number, right? Fibonacci number. So Fibonacci of n, what's Fib n? Anyone, other mathematicians, what's Fib n? What is Fib 4? What is Fibonacci of 3? What's Fib 3? Me, I've forgotten.
3
What's
times
Fib
2
Oh, is it times or plus?
is times.
It's times, right? And it's 3 times 2 times 1,
Yeah.
right? Right.
Yeah.
Okay. So Fib n is equal to what? N times Fib of is equal to Fib of n minus 1, right? And so on, right? So I guess we can define it this way, right? I'm not sure what the operation is, but let's it's plus. Oh, Fib n is okay. So Fib of n is equal to Fib of these ones kind of, but in an interview they'll tell you what it means, so this is no problem. Fib of n minus 2. Okay, so let's assume we have this one, right? And want to solve, we are like find Fib of 10, right? Find Fib of 10. That's basically the whole question. Find Fib of 10. We're going to use both top down and bottom up, right? So we can be like, okay, let's take a number. Let's take the 10 itself, right? So Fib n is 10. Fib n is going to be equal to, so let's Fib n is going to be equal to Fib 9, right? Fib 9, that is n minus 1, and Fib 8, right? Then someone is like, okay, let's compute Fib 9. Fib 9 too is going to be Fib 8. So you can see some repetition now, Fib 7. Right? So this is going to also be, Fib 8 is also Fib 7 and Fib 6, right? And then this is also Fib 7. I mean, people can see where we are going to, right? You can see what is happening. Hope everyone can see what is happening, right? And so on and so forth. So let's see how we can do a top-down approach. So a top-down approach is literally, I feel like recursion, the top-down is like literally the simplest, right? Like the code for this whole thing, right, is simply, one, you need your base case, right? And I think the base case, we can use the base case to be Fib 1. That's Fibonacci of 1. Actually, let's use Fib 2. Fib 2 is our base case, but you also need Fib 1. What's Fib 1? Fib 1 is 1, right? Wait, what's Fib 1? I have no idea. Let's assume Fib 1 is 1, right? Let's assume Fib 0 is 0. Let's just do that. Fib 0 is 0. So that means Fib 2 is going to be 1, right? For now, I know it may be wrong. Let's just do it with this, right? So can just use, so for the recursive case, so let's do top-down first. So top-down approach. Top-down, right? It's simply, just write your base case. If n is equal to 2, return, if n is equal to 2 or n is equal to 1, you can simply return 1, right? And if n is equal to 0, you can simply return 0, right? Let's assume that's all, right? In a recursive case, all you need to do is simply return Fib n minus 1 plus Fib of n minus 2, and you are done. This is a top-down approach, solution to this whole problem, right? Because look at it. Fib n is equal to what I got from Fib 9 plus what I got from Fib 8. And that is basically what you have here. And that is all. You are done. That is the top-down approach, which is usually a very simple and very few lines of code. But the bottom-up, it's not like that, right? Don't think of memoization as we memorize later. But then the bottom-up, right, is different. The bottom-up, we usually start with what we call a table like this, the DP table, right? And then we're going to start it like this. Please look carefully. It's very smart and very cool. Then we can do something like this. Let's divide this into parts. So this is like, we're looking at 10, right? So this is like 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's add 9 and 10. 9. Let's move this guy here and 10, right? Can everyone see this table? We're actually almost done. Can everyone see this table? Can everyone see this table? Can everyone see the dimensions divided? Good.
Yes.
Now, then you put in your base case. Fib 0 is 1, Fib 1 is 1, and this guy is what? 8. No, this is 0. 0, 1, 1, right? Then look at the bottom up one, right? We can start from the bottom from fib 0 and build it up to 10. And all we simply have to do, then now let's start our for loop at this guy here, at the 3 here. All we can do is that we can simply see that fib 3, right? Can you see fib 3 is equal to fib 1, right? Plus fib 2. Can we see it here? Like, that's like the definition of Fibonacci, right? Here, right? That's the definition of Fibonacci, right? But now, instead of calling it fib or whatever, let's assume that our table is called DP, right? We usually call it DP, right? So I can simply say that DP at position at index 3 is equal to the DP at index 1 plus the DP at index 2, right? And before you got here, before you get to you had already filled in your table with these things, right? So this is like a very constant time operation, right? Constant time operation. All you need to do when you get here, just take the two values at the back and just add them, and then you put them in. So here we can simply do 1 plus 1 is 2. We get here to do the same thing. Take the previous two elements, just a for loop, right? Like for I in range n, for I in range, you can do n plus 1. Let's simply do dp of I is equal to dp of I minus 1 plus dp of I minus 2. And you're done, minus 2. So this is the bottom-up approach. You just draw your DP table, and it's your DP table is the equivalent of the memoization table you do when you do the tree one. Because the tree one, the recursive calls are independent. So you see fib 8 here, you also see fib 8 here. So you have to use like a hash map or something. But if you do the bottom-up one, you don't need to bother. That table you constructed at the start is going to act as like your memoization number. So if I need fib 5, if I go to fib 5, I would have computed fib 3 and fib 4, right? DP of 3 and DP of 4, and simply add them and plug in the value here. So this is the top down and the bottom up. Bottom up, we already had these values at the bottom. Then we are simply, just using another recurrence relation and just pushing when we got at some number that is above, we add it at the bottom from the bottom, then we come up, right? But this one is top, then we are going down. Does it make sense? So those are the two ways to solve a DP problem: top down and bottom up. Call next week, we'll do a few problems and just, look at this. But this one question that you can actually use DP for very easily. Okay, we're actually done for today. It's actually time. It's 9 p.m. I know it's a lot today. Rewatch the recording if you have to. Take your time. I bet you, like, after learning this, like, you will have a big good. Well, next week we'll do a few problems, and that will really solidify your understanding of DP and a few things. But as I said, DP is like classes of problems, right? So now let's say now we are doing this guy. We've actually done 2 different ones today, but it's fine. Anyone has any question? Was anyone super confused? Super duper confused? Anyone? Stop share. There was a lot of confusion, right? Yeah. We'll share that.
I wanted to.
Yeah.
I wanted to see that after the session, you can just type the summary of everything on Slack.
Yeah, we're actually thinking about it to create like a 1-page summary notes of everything. It's kind of like a lot of work, like recording it and uploading the recording and everything. Don't worry, that's something we plan to do this summer actually. After every session, we get like a 1-page summary, right? Summarizing everything. Because watching a 1-hour video may not be for everyone. But yeah, just we'll try and work on that, right? But yeah, that's what we mean by DP. We'll go on to the next thing. God willing, next week we'll finish on our matrices. There's actually a few more we have to do on matrices. Then we do maybe 2 DP problems. And yeah, we'll see from there. God willing, next month in July, we'll start with graphs. Because the matrices, as I said, we have adjacent matrices used to represent graphs and everything. And I feel like graphs are one of the easiest data structures you can do. Like the pattern is like there's a pattern, right? And you know the pattern and you're good. All right, people, let's meet God willing next Sunday. We'll upload the recording as early as possible. If you have any other questions, let us know in the channel. Okay, bye. Wow, and no buyback.
Bye.
Bye. Oh,
Bye. Bye. Thank you.
Africans, Nigerians, all of them. Okay.
Bye, BB6. Bye.